Over the past couple of videos, we've been taking a look at ionic compounds and ions. Now, in this video, what I want us to take a look at is the different properties which ionic compounds tend to have. And the first property I'd like to look at is electrical conductivity. Electrical conductivity. And what I have here is a diagram which basically represents what happens when ions are in the lattice, well, in a solid ionic lattice, and what happens when ions have either melted or dissolved. Now, ions, when they are in their solid form, as you can see here, are in a sort of organized regular structure, and the ionic bonds keep them from moving. Not only that, but the ionic bonds also prevent the electrons from moving also. So there's no current is able to pass through this because of the fact that the electrons are in a fixed position, as well as the ions. And so when ionic compounds are solid, they're not conductive, not conductive. They do not conduct electricity when they're solid. Whereas when you melt them, what happens is something changes. The ions are now free to move around. They can move to the left, they can move to the right, up, down. They can move in different directions and bounce off each other and move from positive terminal to negative terminals, and basically allow electrical charge or electrical current to flow. And so therefore, when they're molten or in aqueous solution, and that means when they're dissolved in water, so either they're melted or dissolved in water, at this point they do conduct electricity, so they are conductive. So as a solid, they're not conductive. Whereas as a liquid or aqueous, they are conductive. And yeah, that's how electrical conductivity, because ionic bonds are really strong, so in this state electricity does not flow. So moving on to a different property, the melting and boiling points of ionic compounds. Melting and the boiling points of ionic compounds. And well, as I said just now, ionic compounds have very strong ionic bonds between the different ions present. The electrostatic forces are strong, and these very strong electrostatic forces have to be overcome in order for melting or boiling to occur. And because they're so strong, a lot of energy is needed to make this happen. And so the melting and boiling points are really high. The melting point is 801 degrees centigrade, and the boiling point is 413 degrees centigrade. So those are really high for pretty much all ionic compounds. Now, the melting and boiling points can vary depending on the type of ionic compound which is present. This particular one here, as you can see, these are the properties of sodium chloride. And sodium chloride, as you can see, has a very high melting and boiling points. But there are even stronger compounds that exist. And the reason why these other stronger compounds have stronger forces of attraction between them, and therefore have higher melting and boiling points, is because they have a different layout, so to speak. So they have different charges. Well, not different layout. I mean different properties. They have different properties. So if you took, for example, a magnesium oxide, MgO, magnesium has a 2+ charge, and oxygen has a 1-, 2- charge. Now, if you remember from my video about ionization energies, the equation which displays the force between two charged particles was F equals KQ. Well, I could anyway, KQQ over R squared. Now, R squared isn't too relevant, right? Well, actually, it's very relevant. Never mind, it's relevant. It's very relevant. This is the Coulomb force equation, by the way. This Q represents the charge on one of them, one of the charged particles, and the other Q represents the charge on the other charged particle. And this R squared here is the distance between the two charged particles. All right. Now, when we have two particles which have a 1 plus charge or 1 minus charge coupled together, so this NaCl, Na has a positive charge and chlorine has a negative charge. And so when they are attracted to when these form ionic bonds, when Na and Cl form ionic bonds, Q and Q, let's say that they are 1. So this would be 1. And yeah, so with what we do with this equation is we take the positive value, by the way, so the magnitude, just the magnitude of those two multiplied. And so you can imagine if we took these two values of charge and put them in this equation, F would be reasonably high. It'd be quite high, obviously, because it's an ionic compound. But if we were to put these two values in the equation, 2 plus and 2 minus, which are both of higher magnitude than these two values, F would be even larger. So with a greater charge, what happens is the force between the two charged particles, so Mg and oxygen, increase by a lot. And so Mg and oxygen, as you can imagine, have much higher melting point, and MgO has a much higher both melting and boiling point than sodium chloride. Because of this, something else which can affect this force of attraction between the two ions in ionic compounds, or however many ions, is the atomic radii. So if we have a compound with a large atomic radii, like if you go down the halogens, for example, right? So we have fluorine, chlorine, bromine, iodine, and astatine. Now, if we want a one-to-one relation, like one-to-one bonding, so one of these with one of something else, we would want to bond these with group 1 elements. So let's take sodium as the thing it bonds with, just as an example. Sodium, so we have an Na. NaF has what I'm wanting to focus on here is the radius, the atomic radius. As you go down the period, what happens is there's more and more shells, and when you have more and more shells, the outer shells are going to be further away from the nucleus, and because of this, the distance between the nucleus and the outer regions of the atom, so the furthermost electron, is going to be quite large. So the atomic radius is going to be large, basically. And so as you go down, the atomic radius increases. And if we go back and if we go back to the equation down here, it says that as the distance increases, the force decreases, because you divide that stuff by the r squared, which is the distance. So as the distance across an ion, a particular ion, increases, there's gonna be less of a force of attraction between the two ions. And so as the radius decreases, R is going to decrease and the force is going to increase. So if you were to bond, going back to that example, if you were to bond sodium with fluorine, the bond between these two molecules, since fluorine has a relatively small atomic radius, the force between sodium and fluorine is going to be much, it's going to be, well, not much, but it's going to be significantly stronger than the bond between, say, sodium and iodine, for example. So NaF, since its fluorine is up here, is going to be much stronger than NaI, because iodine has a large atomic radius. Now, going back to the properties, So yeah, but in general, yeah, ionic compounds tend to have high melting and boiling points. Now, there's another property which ionic compounds have, and that is the fact that they are usually soluble, especially in water, which is a polar liquid. It has dipoles and slightly positive and negative charges. So if you were to put an ionic compound inside water, so if we take sodium chloride, so NaCl, NaCl. Okay, this is repetitive. Cl, Na, Cl, Na. So if we were to take an ionic compound like this, for example, bearing in mind that sodium is positive and chlorine is negative, what we know is that the water molecules are polar. And so if I was to draw a water molecule here, we'd have oxygen, which is slightly negative. So that oxygen is slightly negative, and we use this symbol to represent slightly negative dipole with the negative dipole. And this is bonded to hydrogen, which is slightly positive, because oxygen likes being greedy with its electrons. So these hydrogens are slightly positive. And so what happens is these water molecules are obviously, since this compound, let's say we place this compound inside water, obviously these water molecules would be all over the place, and they'd probably be bumping into this compound because the compound is in water. And what happens is, due to the forces, due to the charges on these molecules, or this molecule and these particles, what happens is the oxygen, which is negatively charged, is attracted to the sodium, which is positively charged, and vice versa. The sodium is attracted to the oxygen. And so what would happen is that this sodium would basically break away from the compound and associate with that oxygen. It would be attracted to the oxygen. And the same thing would happen with the chlorine. What would happen is the hydrogens from the H2O would come along, and it would basically be attracted to it like that. So you have these slightly positive hydrogen atoms, and this chlorine would be pulled away, just like the sodium. It gets pulled away, and in this way, as they continually get pulled away, it eventually becomes a dissolved compound. So the compound dissolves in water. And so because this process happens, we say that the compound is relatively soluble in water. And this is why. So yeah, those are the three main properties with respect to the ionic compounds. And just like I said with the whole melting point and boiling point thing with NaCl and MgO2 being stronger, the same sort of thing applies to this, because there's a force of attraction between these, and these oxygen not oxygen molecules, these H2O molecules need to overcome that force to break apart this lattice. So that sort of comparison comes into play here as well. So that's basically the property, like a summary of the properties. So I hope this video was helpful, and I'll see you in the next video.